Up to now, we've been dealing with only, two objects that were colliding. So you would have two carts that would collide, or you'd have two things explode apart, and you would conserve momentum when there was a collision. Now we're going to just take a look at something called the change in momentum, and what's important is that it is for only one object. Because as we know, in a collision, the whole system theoretically did not change momentum at all. But when we look at just one of the objects in the collision, there is a change in momentum of that object. So change in momentum is equal to the final momentum minus the initial momentum, not difficult at all. Final and initial momentums may be in the same direction, they might be in opposite directions. But what's really important is to keep an eye on these signs and keep direction in your mind. So let's take a look at how these unfold. A billiard ball has a mass of 1,5 kilograms. It moves 3 meters per second to the left. So what's its starting momentum? Its starting momentum is 1,5 times by 3. That's the initial momentum, and I'm going to make the left positive. Strikes the cushion at the edge of the table at right angles and bounces back or rebounds at 2 meters per second to the right. So the right is going to be negative. Same mass, negative. Notice there's a minus sign here. Final momentum minus initial momentum, and I land up with a minus and minus again, and therefore you get negative 0,75 kilogram meters per second. Notice what that negative means. You need to interpret it. It means to the right. So we're just going to calculate the change in momentum of a single object. How does this what's important about this is that it starts to link into Newton's second law. In that, we can now start taking a look at a quantity known as impulse. And impulse is the change in momentum, but change in momentum is also equal to force times time. In other words, there are two ways of working out the change in momentum. And I'm just going to derive this quickly for you. Force, you all know, is mass times acceleration. You know that acceleration is equal to final velocity minus initial velocity divided by time. Not difficult. So instead of A here, I'm going to substitute in that expression. Notice what has happened now. I've got mv and mu. And if I multiply both sides by time, I get Ft is equal to the change in momentum. Force times time is change in momentum. Notice, impulse is a vector quantity. We are going to have to worry about direction. Impulse is equal to change in momentum, which is equal to the average force during whatever change occurred during the collision, multiplied by the time. And since force is in newtons and time is in seconds, kilogram meters per second is the same as Newton seconds, which we discussed when we did momentum anyway as a question. So we've got a rifle. It has a mass of 5 kilograms. It fires a bullet of 0,03 kilograms, or if you like, 30 grams, at a certain speed. What is the impulse, in other words, the change in momentum experienced by the rifle? Impulse is change in momentum. We are only interested in the rifle. However, we're not given a lot of information about the rifle. But it is interesting that whatever the change in momentum is of the rifle must be the same as the change in momentum of the bullet, except in the opposite direction, because let's not lose sight of the fact that this would have been an explosion. So here's my gun, and here's, oh, what a beautiful gun. And there's my bullet, and at the moment of explosion, we would have had a certain momentum going in that direction, and there would have been a recoil or a kickback on the gun. So I can work out the impulse experienced by the rifle by working out the change in momentum of the bullet. So let's do that. I take the bullet's mass, I say final velocity minus initial velocity, final velocity minus, the whole thing was stationary at the beginning, and I get 45 kilogram meters per second. That's the momentum change of the bullet. But the rifle is equal but in the opposite direction. So in other words, the impulse experienced by the rifle is equal to 45 kilogram meters per second in the opposite direction to the bullet. What about the average force that the rifle exerts on the gunman's shoulder, assuming that the firing process occurs in 5 times 10 to the negative 2 seconds? Average force is equal to change in momentum divided by time. Remember what the equation was? Ft is equal to change in momentum. So I can divide both sides by time and rearrange that equation. I've got a change in momentum. I've been given a time. And therefore I get 900 newtons against the rifleman's shoulder. Now, what's interesting is now that we know a bit about momentum and impulse, we can restate Newton's second law and Newton's third law. The first one is Newton's second law. Remember what it was? F is equal to ma. We had that if an unbalanced force acts on an object, that object will accelerate. That acceleration will be directly proportional to the force and inversely proportional to the mass of the object. Another way of saying that is that force is equal to change in momentum divided by time. So, when an unbalanced force acts on an object, the rate of change of momentum, rate of change divided by time, change of momentum is equal to that unbalanced force. What about Newton's third law? The change in momentum experienced by each body is equal in magnitude but opposite in direction. This is also true of the impulse on both bodies. So, in other words, remember, change in momentum is mass final velocity minus initial velocity of the one object. It says the change in momentum by each body is equal but opposite in direction, so I'm going to change the direction by changing the sign. That's the change in momentum again, mass final velocity minus initial velocity. But what do I know about change in momentum? Change in momentum is equal to Ft. Force on the one object, force on the other object, times time, but they're in opposite directions. And since whatever explosion, whatever collision took place must have taken place over the exact same period of time, I can cancel the times out, and I find that this sounds a lot like Newton's third law as we learned it last year, which is that for every action force, there is an equal but opposite reaction force on a different body.